obviously epsilon. For epsilon 0, the output, the probability of the output of m on x and x prime exactly the same. But what is the relation of this similarity with the privacy? So we can explain it with a simple randomized response example. So if you want to run a survey to know how many people, for example, are illegal drug users, so if you directly do this one, you cannot find some true answer. So the people may just give you the wrong or answer, so they don't give you the true answers. Instead, for example, you can randomize and you can ask the people to flip the coin. If the head's coming, tell the truth, yes or no. If the tails, for example, coming, so again, flip another coin, and then on head and tail, they can give you yes or no. So in this case, if you quantify the probabilities, for example, the probability of the yes as the output of m, if the answer is truly yes, is 75%, for example, or for the true answer no is 75% as well. And 25% is for the probability of no or yes if the original answer is different. So here in this simple example, 75% is 3 times bigger than 25%. If you choose e to the power of epsilon equal 3 or epsilon 1.1, you can simply have a randomized process, which is a purely epsilon differentially private, a very simple example. If you want to generalize this, for example, to quantify the attacker's knowledge, say you assume that the attackers have the initial guess if its targeted person is in the database or data set or not. So that's the probability of that. And then the attacker wants to update his or her guess based on the output of the randomized process. So for example, how much probability is the person in that data set? So you can visualize this probability based on different values of epsilon. For example, for epsilon 0 here, you don't have any updated guess, but for epsilon 1.1, you can have an lower bound and upper bound. Say, for example, for initial guess of 50%, you can have a chance of corrected updated guess of, say, 25 to 75%, for example. In general, if you want to derive the formula for quantifying the attacker's knowledge, you can do it by Bayes' rule. To find the upper bound and lower bound of the updated guess based on the assumption that you know the output of the randomized mechanism on X. So if you visualize this for different values of epsilon, visualize updated guess versus initial guess, you can have this kind of curves here. And as you see, for large values of epsilon, so the degree of certainty is growing quite fast. For example, with 10% of initial guess, you may reach to the updated guess, the corrected updated guess with a probability of 94%. So this is something that you can get here. Now, we talked about the pure differential privacy epsilon. Now we want to talk about approximate DP and zero concentrated differential privacy, or for short ZCDP. So this is the definition of the approximate DP. If you have a randomized, again, mechanism, we call it, this randomized mechanism is epsilon delta differentially private for all neighboring data sets, which are differing in only one element. We call it X and X prime. And for all elements, if we have this inequality in terms of the probability of the output of the randomized mechanism applied to X and X prime. But here we add delta. Delta is a value that represents a probability, and in this case, delta accounts for bad events, for bias or outlier that might result in high privacy losses. For example, if you want to have an ideal mechanism like with the uniform distribution, for example, for a data set of the size of n or n people, then that mechanism is 0 and 1 on n differentially private. So in that case, we need to take delta much smaller than 1 on n, and n is the size of data sets to have, say, for example, lower privacy loss, or say lower chance of outlier or bias. For instance, US census in 2020, when it switched to the Gaussian mechanism, used the delta around 10 to the power of -10. So, which is a much small value in terms of the magnitude. Now, let's talk about the output perturbation mechanism. Before that, we need to define global sensitivity. For any query function Q, which is defined from xn to rk, we define delta P as the supremum of the difference or the difference between Qx and Qx prime. So when you call the query for x and x prime. And P here is depending on the mechanism. For example, for Laplace mechanism could be 1, for Gaussian could be 2. Now, the two widely accepted mechanisms or output perturbation mechanisms are Laplace and Gaussian. For a single query, here we briefly presented those ones. The Laplace mechanism is when you add the noise to the query, if you've got the randomized mechanism M. And this noise is drawn from the Laplace distribution with location 0 and a scale lambda. Now, if the scale lambda is delta on epsilon, we can say this mechanism, Laplace mechanism, is purely epsilon dp. But if you choose y from Gaussian mechanism with this, for example, scale or standard deviation, we can say this Gaussian mechanism is epsilon delta dp. So here we can see the PDF of Laplace distribution, and as you see, when we increase the scale parameter from 1 to 2 to 4, the tail becomes heavier, and that's creating problem and in terms of bias, outlier, and say, for example, challenges for the post-processing of data. So that's why we want to see if we can have the distribution that have the lighter tail than Laplace distribution, which we call it, say, for example, this distribution is sub-Gaussian, for example. Now, let's have a look at the privacy loss here. So, in order to find delta for approximate differential privacy, we can have the privacy loss function like defined here. The privacy loss function is logarithm of the ratio of the two PDF of the randomized mechanism. And then if you apply this on MX itself, we call it privacy loss. And based on that one, we can say, for example, determine delta based on the probability of the privacy loss, if it is greater than epsilon, or say, if you've got probability of L prime less than or equal to negative epsilon or something like that. So in fact, for a Gaussian distribution, we cannot have the pure epsilon dp, and as we mentioned, we need to have delta. It's not possible. We talk about that later on. First, in terms of the analysis of Laplace mechanism, if we have the query function of x1, we want to add y, or noise from Laplace distribution with this scale function to this query. So in order to find delta, we need to find the critical point of y, below which, for example, this ratio is not valid. So simply if we take qx without loss of generality, we take qx0 or qx prime delta, then we need to find the worst case set. We call it E star. And those sets are including the y values for which the privacy loss, for example, is greater than epsilon, or the ratio of the probability distribution function is bounded by e to the power of epsilon, or say, for example, below which you couldn't have those inequality valid. So in this case, for Laplace mechanism, we can get this one, but for Gaussian distribution, if you choose y from Gaussian distribution, there is no finite epsilon for E star, so we need to have approximate dp or ZCDP. That's why for Gaussian mechanism, we need to have approximate dp or ZCDP. And if we want to find the worst case set, to find delta, instead of directly finding the worst case set and then derive delta, we need to, this is equivalent to find the answer of this integration on the worst case set of E star. And because this integration depends on the CDF function or cumulative distribution function of Gaussian distribution, that's why you can see the function delta in terms of epsilon depends on the Gaussian Q function. So again, this point is the critical point. So for below which, for example, that here, this inequality cannot be satisfied. And here, our purpose is to show that can we, for example, push this one further back to have better delta in terms of the, say, for example, reducing the chance of outlier or not. So, and then we will see that in the OSGT, we can do that one. Another useful concept in differential privacy is zero concentrated differential privacy, or ZCDP, which can give us better control to find the parameter and the performance of the differential privacy. So here is the formal definition of ZCDP. If you have the randomized mechanism M, we say this is zeta rho, zero concentrated DP mechanism for X and X prime if the Rayleigh divergence of the M on X from M on X prime is bounded by zeta plus rho alpha. And this is the definition of the Rayleigh divergence of two distribution with order alpha. So we can show that Gaussian mechanism achieves delta squared on 2 times sigma g squared ZCDP. And if you set, for example, sigma squared g equals to delta squared on epsilon s squared, then Gaussian mechanism can achieve 1 and 2 epsilon s squared ZCDP. So what are the limitations of Laplace and Gaussian mechanism? And that's the motivation to say, for example, propose this new mechanism. So We know that Laplace mechanism can reach epsilon dp, but it has heavy tail, as we see, for example, here. Its tail is heavier than Gaussian mechanism. On the other hand, Gaussian mechanism has sub-Gaussian tail, so it means it has lighter tail than Laplace distribution, but it cannot achieve pure epsilon dp. That's a drawback for that, and it can only achieve the approximate epsilon delta dp. Now, and that's the main motivation, for example, for the US census that switched to from Laplace distribution or discrete Laplace mechanism to Gaussian distribution in 2020. Because of the heavy tail, say, for example, in case incurs more bias outliers, the chance of these ones. And in fact, in terms of delta, finding delta, which incurs less outlier, we want to push this point further to the left to get lower values for delta. Is it possible to do that one? Yes, it is possible in AusCTW, which we propose that. Okay, now let's introduce the AusCTW distribution, which we say later on, and we see it has better performance than its counterpart, Gaussian mechanism. Offset-symmetric Gaussian tail distribution, or for short AusCTW. This is the definition of the probability density function. So you've got input parameters m and sigma, and this is the definition of the PDF for AusCTW. And as you observe here, two tails, like this tail and this one, of two Gaussian distribution located at negative m, like that, and m, just they build the AusCTW distribution. And this is a normalization factor S, depending on the Gaussian Q function, which takes care of the area below these curves. So if a random variable y follows the AusCTW distribution, we can denote that one with t, 0, location 0, this is located at 0, and with variance v, which is depending itself on m and sigma square. And sigma square is the original variance of the two Gaussian distribution that contribute to building this distribution itself, and with location m. But there's another way to represent the formula of the PDF for AusCTW. So if you consider this Gaussian and you modulate it by the Laplace distribution with different normalization factor, it is still the AusCTW PDF. And even you can write it in different format like this one as well. Why we write it in this format? Because we want to show that AusCTW is a kind of distribution that is behaving between Gaussian and Laplace. It's a hybrid behavior. It combines the hybrid behavior of Laplace and Gaussian distribution. So, for example, if the absolute value of y is much smaller than 2m here, you can achieve a scaled version of Laplace PDF with location 0 and with scale of sigma square on m. On the other hand, if m on sigma is much smaller than 1, it's very small, the AusCTW PDF approximate the Gaussian PDF at location 0 with scale sigma. So that's why it's a hybrid behavior. It has a hybrid behavior between Laplace and Gaussian. Now, let's have a look at features or properties of AusCTWs, which are characterized by the parameters variance, tail, or these kind of things. But before that, we need to mention that generally in an output perturbation DP mechanism, the lower the variance of the noise, the higher the utility of the mechanism. That's why if we have a random variable y, which is following the OSGT distribution with variance v, depending on parameters m and sigma squared, we can show that the variance of that random variable has this form, and it can be proved that it is less than sigma squared, which is the variance of the original Gaussian distribution, which contributes to the shape of the OSGT PDF. And here you can see some numerical example here. This is a sigma squared for the variance versus sigma squared. This is the sigma squared itself, and that's the variance of OSGT for different values of m, for example, for m3 and m5. And as you see, if you increase m, you will have a further gap with the original sigma square, which is good. What about the shape of PDF and tail of OSGT? In general, as we mentioned before, a lighter tail will reduce the chance of the outlier. So that's why that was the main motivation for switching to Gaussian distribution from Laplace by US Census in 2020, because they realized that the Gaussian distribution has a lighter tail than Laplace distribution. So here in this figure, you can see that the three PDF corresponding to the Laplace, the green one, and the Gaussian one, the red one, and the blue one is OSGT. And as you see here, for a smaller value of y, we can see that we have a scaled version of Laplace distribution represented by OSGT, which is good. And then, as you see here, it is still behaving like the sub-Gaussian with the rate of sigma squared. So it means OSGT has lighter tail than Laplace distribution, but heavier tail than Gaussian distribution. But this heavier tail of OSGT than Gaussian distribution could be justified later on why it just gives us the better performance, in fact. Now, let's have a look at the privacy performance of OSGT mechanism. And in particular, we compare this performance with its counterpart, Gaussian distribution. So first, the approximate DC performance of a single-dimensional OSGT. So in this theorem, gives the delta versus epsilon, or as a function of epsilon, for OSGT. So you've got a query M applying to dataset X, the randomized M applying to dataset X. That's the combination of a query plus the noise. The noise is drawn from the OSGT distribution with variance V depending on M and sigma squared. And we can say this OSGT mechanism is epsilon delta differentially private with this delta as a function of epsilon. To have a better intuition, because this is a very complicated formula, to have a better intuition about this formula, we can say that the noise which is adding to the query is following the OSGT distribution. So again, like Gaussian, we need to find the worst case set for which values of y can be found in a way that the ratio of the probability distribution function bounded by e to the power of epsilon. And this is, as we mentioned, this is equivalent to finding this value of this integration on this worst case set. And if we analyze this, we can realize that so if you look at this, for example, for simple example like this distribution, that you have qx prime is bigger than qx, and then you've got delta q, the difference between these two locations. So we need to find E star, we need to look at these shaded areas because we know that in this wide area, so it's not possible to have this ratio satisfying this inequality, or we cannot find the y for which this probability density function is bigger than that one. That's why we need to focus on this and then finding those ones. But because this integral itself depending on CDF function of OSGT and consequently depending on the Q function, so you can see this kind of formulation here. But again here, the question is that, as we mentioned in the analysis of the Gaussian distribution, we said we need to find y in a way that below which, for example, we have we need to find the values of y or the critical, for the critical point of y below which, say, for example, we have better delta. So here the question is that can we find a push further the critical point from this y to the, say, for example, green y. So for OSGT, this is possible. So in fact, this Laplace-like behavior of PDF, which is close to mean, as you see here, can push further out the critical point to the left, which consequently giving us a smaller delta than Gaussian distribution. So, for example, we can see in the performance comparison that in some cases, so the delta of OSGT at the same variance when you compare it with the delta of Gaussian has the is much smaller by, say, for example, an order of 3 magnitude. For example, here you can see the numerical comparison of OSGT and Gaussian distribution for different values of sigma square, as you see, for 40 and 20, and for this range of epsilon for both figures, you can see OSGT can give you better performance in terms of approximate differential privacy. What about the zero concentrated differential privacy for OSGT? For OSGT, we can achieve the ZCDP with this parameter rho and zeta, and we can have some insight into this ZCDP or the performance of OSGT as well. So we can say that for almost large enough alpha, the ZCDP of OSGT mechanism can approach rho ZCDP for large alpha, or for M on sigma very small, because this is approaching 1. Again, zeta is 0, so we can recover the ZCP with Gaussian distribution, which is what we expected. And in general, for the same 2 query sensitivity, we can say that rho, which is the parameter here for ZCDP of OSGT, is less than the rho that you can find for the Gaussian distribution. So in fact, for sufficiently large alpha, when we can ignore the effect of zeta, so the ZCDP performance of OSGT is superior to the Gaussian mechanism, but at the same variance to, or maybe covariance metrics for multi-dimensional queries. And if we want to compare the ZCDP of Gaussian and OSGT, this is for the single dimensional case. So we can have here this red curve. So that's the Renyi divergence versus alpha. So for Gaussian, you can have the red curve, which is representing the rho ZCTP of Gaussian mechanism at the same variance with AusCTW. And this blue curve here, that's the numerical calculation of the Rayleigh divergence. And this dashed green line is the upper bound of this Rayleigh divergence. And as you see here, it shows that the AusCTW in ZCDP also performing better than Gaussian distribution. But as you see here, for smaller values of alpha, we've got this shape of the green dash, which shows the artifact of our proof technique that we used for finding the upper bounds. So also, I didn't include the detailed multidimensional analysis of AusCTW because it just incurs complicated formulas, but it is available in our archive paper. You can refer to that one. I just only wanted to mention, because for multidimensional queries like K, when K is greater than 1, it's challenging to find the exact value of delta directly versus epsilon for AusCTW. That's why we convert, say, for example, the approximate dp to the z CDP, and then we found the performance of the multidimensional queries of AusCTW. And here I only presented the one numerical value for the concentrated dp of AusCTW, and also Gaussian mechanism for the query of 8. And as you see here, the multi-dimensional version of AusCTW even performs better than Gaussian mechanism, which shows the superiority of the AusCTW mechanism on Gaussian mechanism. And finally, some conclusions. So we talked about the differential privacy. We said differential privacy can give us a precise quantification of the privacy utility trade-off, because we cannot have absolute privacy or zero privacy loss. So it's also robust against powerful adversaries, even in the presence of the side knowledge. Even if the attacker wants to find particular element or person in their the data set, if they have side information or knowledge of data set, it's not easily possible. And also it can be applicable to a wide range of application, as we mentioned, using now by big companies like Google, Facebook, Microsoft, Apple, and also in data analysis, deep learning, and different applications, and particularly in census application as well. So we talk about the limitation of the two perturbation mechanism, Laplace and Gaussian. And based on this limitation, we said that is it possible to say propose a mechanism which is behave something similar to Gaussian distribution but performs better than that. So that's why we proposed a novel output DP mechanism, call it AusCTW, and we showed that in terms of the differential privacy protection at the same variance, AusCTW can perform better. For some future direction research, we are going to have some experiments on the real or synthetic data set using, say, for example, multi-dimensional version of AusCTW mechanism. And more importantly, because AusCTW has a potential to be used in census application, we are going to fully develop the discrete version of AusCTW, which can be used in in the counting queries. And in fact, we have done some preliminary work on discrete version, but it is unpublished. Okay, so that's from me. Thanks very much for listening to the presentation, and I appreciate your time. And I also would like to